Hi class, here's a short video on electromagnetic waves and using scientific notation to represent their wavelength. And in this opening picture, we see a cartoon of a glass prism. And what a glass prism is useful for is you can take a beam of white light from something like the sun, and you can actually spread it out into its spectrum. And you can see that this white light is actually composed of the various colors of the rainbow from red to violet. And these are all examples of electromagnetic waves, which you read about this in chapter 5 of our textbook. This was discovered in the 1860s by James Clerk Maxwell. That light is actually an electromagnetic wave. It's a self-propagating wave composed of electric and magnetic fields, which is very interesting. And he also realized that you can produce these electromagnetic waves with any size or wavelength. We use this Greek letter lambda to represent that. And all of these electromagnetic waves, regardless of the wavelength, they all travel at the same speed, which is 300 million meters per second. So this is one way to visualize an electromagnetic wave. Keep in mind that they come in all different sizes. Here is a picture from our textbook that represents the various types of electromagnetic waves: radio, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. The important thing to keep in mind is that these are all the same exact thing. They're all electromagnetic waves. The only thing that's different is that they have different wavelengths. So radio waves are the biggest electromagnetic waves. Any electromagnetic wave which has a wavelength greater than about 10 centimeters, we call it a radio wave. And the waves that are approximately between 10 centimeters and about a millimeter, we call those microwaves. Things that are smaller than microwaves but longer than red light, we call that infrared radiation. This is a pretty wide range right there. There's the visible spectrum from red to violet. These are the electromagnetic waves that we can see with our eye, so that's why we call it visible. And then shorter than violet is ultraviolet, shorter than ultraviolet is X-ray, and finally shorter than X-ray is gamma ray. And you notice that down here we're given the wavelength of these various forms of electromagnetic waves. And these are all pretty familiar units right here. You have the kilometer, you have the meter, the centimeter, and the millimeter. And I'm assuming you have encountered these units of measurement at some point in your life. Millimeter is quite small. Centimeter is it's a little bit less than a half an inch. A meter is pretty close to a yard or 3 feet. It's like arm's length. And then a kilometer is a little bit less than a mile. So these are all kind of familiar units of measurement. However, when we get into infrared and visible and ultraviolet, and certainly as we get into X-ray and gamma ray, we start encountering wavelengths which are very, very small. So we want to use a unit of measurement that is more appropriate. So we use something that's smaller than a millimeter. We use a micrometer for infrared light. And then when you get into visible light, you start to use a different unit, which is called the nanometer. So I want to explain what those are in this video. When you talk about radio waves, they're pretty big, so we can just use meters or kilometers to describe those. So for example, if you listen to the radio and you tune into an FM radio station, pretty much all FM radio stations are about 3 meters in size. And if you dial into AM radio waves are about a quarter of a kilometer. So about 250 meters, although there's a range, but that's a typical AM radio station's about a quarter of a kilometer. When you talk about microwaves, you probably think of your microwave oven, which does use microwaves to cook your food, but a lot of other things use microwaves. For example, your cell phone uses microwaves to communicate with the cell phone tower. Wireless internet uses microwaves, and you can use microwaves of different wavelength. But When we talk about microwaves, we're talking about electromagnetic waves that are smaller than radio waves. They're smaller than 0.1 meters, and they're larger than about a millimeter. That's a millimeter is a thousandth of a meter. So these are the two longest forms of electromagnetic waves, radio and microwaves. And then as we get into infrared and visible and so on, now we start to use these new units of measurement. So a millimeter is a thousandth of a meter. So there's the millimeter right there, 0.001 meters. A micrometer, sometimes called a micron, we use this Greek letter mu. The M has already been used up for millimeter, so here we use mu, which kind of looks like a U, but it's a mu. Micrometer is a millionth of a meter, 0.000001 meters, and a nanometer is a billionth of a meter, 0.00000001 meters. So and this is quite cumbersome to write all these zeros, and that's why we use scientific notation. So in scientific notation, we would represent a millimeter, which is 0.001 meters, as 10 to the minus 3 meters. And the reason is that we would take the 1 and you'd move the decimal place 3 spots to the left. So that's the meaning of that 10 to the minus 3 meters. It means you take a 1 and you move the decimal place 3 spots to the left. Similarly, for a micrometer, you would take a 1, which would have the decimal place after it, and you'd move the decimal place 6 spots to the left, and you get a micrometer, 10 to the minus 6 meters. And finally, for a nanometer, you would move the decimal place 9 spots to the left to turn it into a decimal number. So 1 nanometer, which is going to be a unit that we use quite a bit in astronomy, is 10 to the minus 9 meters. So when we talk about the visible spectrum from red to violet, we're talking about electromagnetic waves that go from 700 nanometers, which is what red light is, down to 400 nanometers, which is what violet light is. So starting with red has a wavelength of 700 nanometers. We can replace nano with 10 to the minus 9. So 700 nanometers is 700 times 10 to the minus 9 meters. 10 to the minus 9 just replaces the nano right there. And then finally, to put this into decimal, we can move the decimal place 9 spots to the left and you get this. Yeah, I started with the 700 and I moved the decimal place 9 spots over to the left. These are all the same number, though the same value. 700 nanometers is equal to 0.000000700 meters. Okay, so you go from nanometers to meters. We can do a very similar thing for violet light, which is at the short end of the visible spectrum, and violet light has a wavelength of 400 nanometers. So, doing the same thing, you can replace nano with 10 to the minus 9, and then you move the decimal to put it into decimal notation, get rid of the 10 to the minus 9, you'd move the decimal place 9 spots to the left. And so there's violet light in decimal. And here's one last example which talks about some other aspects of light that you read about in chapter 5, which is the photon description and how light is emitted by atoms. So make sure to read about that in section 5.8 of the textbook. But here it is in astronomy. This is something that we'll be studying next week. This is called a planetary nebula. This is a dead star. There's a very hot exposed core of the dead star, which is called a white dwarf star in the center. And what this is doing is it's exciting these gas atoms out here. And this red light at the edge, this is actually hydrogen gas, which is primarily what we study in section 5.8 of the textbook. And in particular, what's happening right here, when you see this red light, which shows up quite a bit in astronomy, we're going to see it from time to time, that is light from hydrogen, where the electron in the hydrogen atom is transitioning from its n equals 3 state to its n equals 2 state. So make sure to read about that. When it does that, it emits a red photon of light with a wavelength of 656 nanometers. We call that H alpha light, and just like we did previously, we can follow those same steps and we can convert this from nanometers to 10 to the minus 9 meters. And this red light has a wavelength, which is